Hello, everyone. In this video, we will answer an exam about continuity. Part 1. Determine whether f is continuous at x equals c. Number 1.
Is f of c defined? Yes. Does the limit of f of x, as x approaches c, exist? Because the one-sided limits both approach the same number. Yes. Is the limit equal to f of c? Yes. Thus, f is continuous at x equals c. Next figure. Is f of c defined? Yes. Does the limit of f of x, as x approaches c, exist? Because the one-sided limits both approach the same number. Yes. Is the limit equal to f of c? Yes. Thus, f is continuous at x equals c. Next figure. Is f of c defined? No. Does the limit of f of x, as x approaches c, exist? Because the one-sided limits both approach the same number. Yes. Is the limit equal to f of c? No. Thus, f is discontinuous at x equals c. Because at least one of the conditions has not been satisfied. Next figure. Is f of c defined? Yes. Does the limit of f of x, as x approaches c, exist? Because the one-sided limits both approach the same number. Yes. Is the limit equal to f of c? No. Thus, f is discontinuous at x equals c. Because at least one of the conditions has not been satisfied.
Number 2. A. f of x equals negative x, if x is less than 0, and x squared, if x is greater than or equal to 0, with c equals 0.
Solution. First, determine if f of c is defined. F is defined on x greater than or equal to 0, which includes x equals 0. Its value is given by f of x equals x squared. F of 0 is equal to 0. The figure illustrates the graph of f of x. The value of f at x equals 0 is defined, and it is equal to 0. It is represented by the solid point. Thus, f of 0 is defined. Second, determine if the limit of f of x, as x approaches c, exists. Compute the right-hand and left-hand limits. the one-sided limits are equal. Please refer to the figure and that the limit of f of x, as x approaches 0, exists, because the one-sided limits are the same. Therefore, the two-sided limit exists, and it is also equal to 0. Third, determine if the limit of f of x, as x approaches c, and f of c are equal. The limit of f of x, as x approaches c, and f of 0 are equal to 0. F of 0 is defined. The limit of f of x, as x approaches 0, exists, and they are equal. Hence, f is continuous at x equals 0.
b. F of x equals negative x, if x is less than 0, and x squared, if x is greater than 0, with c equals 0.
Solution. First, determine if f of c is defined. F is defined on x less than 0 and x greater than 0 but not at x equals 0. Consequently, f of 0 is undefined. Because x equals 0 is not in the domain of f. The figure illustrates the graph of f of x. The value of f at x equals 0 is undefined. It is represented by the hollow point. Therefore, f is not continuous at x equals 0. Even if the limit of f of x, as x approaches 0, exists.
c. F of x equals negative x, if x is less than 0, 1, if x is equal to 0, and x squared, if x is greater than 0, with c equals 0.
Solution. First, determine if f of c is defined. F is defined on x less than 0, x equals 0, and x greater than 0. At x equals 0, the value of f is f of 0 is equal to 1. The figure illustrates the graph of f of x. The value of f at x equals 0 is defined, and it is equal to 1. It is represented by the solid point. Second, determine if the limit of f of x, as x approaches c, exists. From the example number 2. A. The one-sided limits are equal and are equal to 0. Hence, the two-sided limit exists, and it is equal to 0. Third, determine if the limit of f of x, as x approaches c, and f of c are equal. The limit of f of x, as x approaches 0, is not equal to f of 0. Therefore, f is not continuous at x equals 0.
d. F of x equals 1 minus x, if x is less than 0, and x squared, if x is greater than or equal to 0, with c equals 0.
Solution. First, determine if f of c is defined. F is defined on x less than 0 and x greater than or equal to 0, or equivalently, on all x in the real line. At x equals 0, the value of f is f of 0 is equal to 0. Second, determine if the limit of f of x, as x approaches c, exists. The right-hand limit or the limit from the right of 0 is the limit of x squared, as x approaches 0 from the right, is equal to 0. The left-hand limit or the limit from the left of 0 is the limit of 1 minus x, as x approaches 0 from the left, is equal to 1. The figure illustrates the graph of f of x. The value of f at x equals 0 is defined, and it is equal to 0. It is represented by the solid point. The one-sided limits are not the same. The limit does not exist. Therefore, f is not continuous at x equals 0, even if f of 0 equals 0 is defined.
Determine the continuity given the graph of f. Number 3. F of x equals 1 over quantity x squared minus 5.
Solution. The graph shows that f has infinite discontinuities, which are non-removable discontinuities, at x equals negative square root of 5 and x equals square root of 5. F is discontinuous at x equals negative square root of 5 and x equals square root of 5.
Number 4. F of x equals x cubed plus x squared minus 9x minus 9 all over quantity x plus 1.
Solution. The graph shows that f has a hole at x equals negative 1, which is a removable discontinuity. It means that f is undefined at x equals negative 1. F is discontinuous at x equals negative 1.
Number 5. F of x equals x plus 1 all over quantity x cubed plus x squared minus 9x minus 9.
Solution. The graph shows that f has a hole, a removable discontinuity, at x equals negative 1. Moreover, f has infinite discontinuities, non-removable discontinuities, at x equals negative 3 and x equals 3. F is discontinuous at x equals negative 3, x equals negative 1, and x equals 3.
Number 6. F of x equals square root of x, if x is greater than or equal to 1, and 1 minus x, if x is less than 1.
Solution. The graph shows that f has a jump, i.e., a non-removable discontinuity, at x equals 1 where the formula of f changes. F is discontinuous at x equals 1. Even though f of 1 is defined.
Part 2. Determine the continuity of the following functions. Number 1. F of x equals 6x plus sine of x.
Solution. The limit of f of x, as x approaches c, by direct substitution is calculated as follows. Because the limit exists for any c in the real line, f is continuous everywhere.
Number 2. F of x equals 3 over x minus the cosine of x.
Solution. The limit of f of x, as x approaches c, by direct substitution is calculated as follows. C equals 0 is not allowed because a number divided by 0 is undefined. Hence, the limit of f of x, as x approaches 0, does not exist. That is, f is discontinuous at x equals 0.
Number 3. F of x equals 1 over quantity x minus 4 quantity squared times quantity x plus 3.
Solution. Calculate the limit at any x equals c by direct substitution. C equals 4 and c equals -3 are not allowed because the denominator becomes 0. Hence, the limit of f of x, as x approaches 4, or, as x approaches -3, does not exist. That is, f is discontinuous at x equals 4 and x equals -3.
Part 3. Determine the continuity of the following functions. Number 1. F of x equals the square root of quantity 16 minus x squared, on the closed interval, -4, 4.
Solution. The continuity on the closed interval, -4, 4, depends on the continuity on the open interval, -4, 4, and the continuity at the endpoints x equals -4 and x equals 4. First, continuity on the open interval, -4, 4. Show that the limit of f of x, as x approaches c, can be calculated by direct substitution of x equals c, for any c in -4, 4. Because the limit of f of x, as x approaches c, can be calculated by direct substitution of x equals c, for of any c in -4 f is continuous on the open interval -4. Second, continuity at the endpoints x equals -4 and x equals 4. A. Evaluate the limit from the right at x equals -4. Because the limit of f of x, as x approaches -4 from the right, can be calculated by direct substitution, f is continuous from the right of -4. B. Evaluate the limit from the left at x equals 4. Because the limit of f of x, as x approaches 4 from the left, can be calculated by direct substitution, f continuous from the left of 4. In conclusion, f is continuous on the open interval -4, 4, and continuous at endpoints x equal -4 and x equals 4. Therefore, f is continuous on the closed interval -4, 4.
Number 2, f of x equals -x plus 4, if x is less than or equal to 1, and x plus 5 all over 2, if x is greater than 1, on the closed interval, -2, 6.
Solution. F is a piecewise function over a closed interval, -2, 6. Its continuity depends on the continuity on the subintervals -2, 1 and 1, 6. The continuity at the transition point x equals 1. And the continuity at the endpoints x equals -2 and x equals 6. First, continuity on the subintervals and at the endpoints. f1 of x equals -+4 is a polynomial, which is continuous everywhere. Hence, f is continuous on the subinterval -2, 1, which includes the endpoint x equals -2. f2 of x equals x plus 5 all over 2 is a polynomial, which is also continuous everywhere. Thus, f is continuous on the subinterval 1, 6, which includes the endpoint x equals 6. Second, continuity at the transition point. At the transition point x equals 1, the equation for continuity at a point must be satisfied. The limit of f of x, as x approaches 1, equals f of 1, which entails the following conditions. A. Is f of 1 defined? Because x equals 1 is in the domain x less than or equal to 1 of f1 of x. F of 1 equals 3. Hence, f of 1 is defined. b. Does the limit of f of x, as x approaches 1, exist? The limit exists if the one-sided limits are equal. Because the one-sided limits are equal, the limit of f of x, as x approaches 1, exists, and it is equal to 3. c. Is the limit of f of x, as x approaches 1, equal to f of 1? They are both equal to 3. Hence, f is continuous at the transition point x equals 1. Third, continuity at the endpoints. This is an optional part since it has already been proven in the first part. At the endpoints x equal -2 and x equals 6, the equations must be satisfied. At x equals -2, the limit of -x plus 4, as x approaches negative from the right, is equal to 6. Hence, f of x is continuous from the right at a. At x equals 6. The limit of x plus 5 all over 2, as x approaches 6 from the left, is equal to 11 over 2. Thus, f of x is continuous from the left at b. Finally, because f is continuous on the subintervals -2, 1, and 1, 6, which include the endpoints x equals -2 and x equals 6, respectively, and f is continuous at the transition point x equals 1. It can be concluded that f is continuous on the closed interval -2, 6.
Part 4. Determine the continuity of the function. Number 1. F of x equals 2 sine of x plus 1 over x.
Solution. F can be broken down into two terms. Sine of x is continuous on the real line, as well as the term 2 sine of x due to scalar multiple property. One over x has an infinite discontinuity at x equals 0. The sum property of continuity says that the sum of two terms is continuous on points where both terms are continuous. Hence, f of x is discontinuous at x equals 0. In other words, f is continuous on its domain D.
Number 2. F of x equals x squared times square root of quantity x plus 1 all over quantity x minus 3.
Solution. F can be broken down into three terms. X squared is continuous on the real line. Square root of quantity x plus 1 is defined and continuous whenever x plus 1 is greater than or equal to 0, or x greater than or equal to -1. One over quantity x minus 3 has an infinite discontinuity at x minus 3 equals 0, or x equals 3. The product property of continuity says that the product of two terms is continuous on points where both terms are continuous. Hence, f, the product of the three terms, is continuous on its domain D.
Number 3. F of x equals x minus square root of x all over sine of x.
Solution. F can be broken down into three terms. X is continuous on the real line. Square root of x is defined and continuous for x greater than or equal to 0. One over sine of x has discontinuities whenever sine of x equals 0, specifically at x equals n pi, where n equals 0, positive or negative 1, positive or negative 2, and so on. The difference property of continuity says that the difference of two terms is continuous on points where both terms are continuous. Hence, f is continuous for all x greater than or equal to 0, except at x equals n pi, where n equals 0, positive or negative 1, positive or negative 2, and so on.
Number 4. F of x equals quantity x cubed minus 1 times the natural logarithm of x minus 2 inverse hyperbolic cosine of x.
Solution. F can be broken down into three terms. X cubed minus 1 is continuous on the real line. Natural logarithm of x is defined and continuous only on the interval from 0 to positive infinity, excluding 0. Inverse hyperbolic cosine of x is continuous on the interval 1 to positive infinity. Therefore, using the difference property of continuity, f is continuous on the interval D.
Thank you for watching. Please like this video and subscribe to Professor Reginald's channel to get the latest updates.